Hey folks, in this video we are going to be talking about the mirror equation. The last video was about drawing ray diagrams that we could use to represent the location and size and orientation and type of an image formed by a spherical mirror. The purpose of the mirror equation is to get after that same information but in a mathematical quantitative way rather than using ray diagrams. So, let's remind ourselves of some of the things with our ray diagrams. Here's our object, it's a candle, light rays going in all directions. Two principal useful rays are this red one, which leaves parallel to the principal axis and it reflects back through the focal length. Another useful principal ray is the one that starts going through the focal length and it reflects back parallel to the principal axis. And this point of intersection is where the image of the candle forms. So some assumptions that we're going to set up in our mirror equation. So one assumption is that the mirror is not very curved. So the blue dashed line, we can use that to measure all of our distances because the deviation from the blue dashed line to the mirror won't be very much because it's not very curved. I have the curvature of the mirror exaggerated in this diagram. Let's define some terms. And I'm going to be in the way, I'm going to get rid of the little bubble. All right, so lowercase s subscript o, not a 0 for initial, but a subscript o for object, is the distance from the object to the mirror. It's the object distance. So here's our object, and notice we're tracing that distance all the way back to this dashed blue line using our assumption that the mirror has a very low curvature. The image distance, this s subscript I, that is the distance from the candle to the mirror. H subscript O, that's the height of the object. H subscript I, that's the height of the image. And our last definition here is magnification. So this is a new concept. Capital M is our symbol for magnification, and it is the ratio of the image height to the object height. So we think about it as a percentage. So ignore the last part here, just look at the first part of the equation. If your image ends up being taller than your object, that's a magnification bigger than 1. If your image ends up being smaller than the object, that's a magnification less than 1. And so the magnification is the percent size of your image compared to your object. If the image is bigger, your magnification is magnified more than 100%. If your image is smaller, it's magnified less than 100%. If it's the same size, we call the magnification just 1 or 100%. So those are our definitions. Let's jump into the mirror equation. So same idea. The last thing I want to throw in here is I've labeled the focal length lowercase f. That's the distance from the focal point, capital F, to the mirror. So this focal length is lowercase f. I'm going to tell you the equation, and then we're going to go through the derivation together. Here is the mirror equation. It is very simple to write, simple to use. A little bit simple to use. It's got the weird inverses, but the equation is this. 1 over the object distance plus 1 over the image distance equals 1 over the focal length. Now, let's derive this equation. Where does this come from? So, math time. Oh, I don't have my focal length labeled here. That's okay. I think the diagram gets cluttered in a bit. Let's label some other things. I want to draw in this fictional triangle. Our proof of the mirror equation is going to come from geometry and similar triangles. And I want to label this distance from the object to the center of the circle with an x subscript O. I also want to look at this blue triangle where the distance from the center of the circle to the image is labeled x subscript I. And I want to finally remind you that the distance from the center of the circle out, that's the radius of the circle. Now, with that diagram set up, let's go. The angle, we're not done with the diagram, just kidding. The angle in the purple triangle here we'll name alpha, and because vertical angles are congruent, alpha also lives at this point in our blue triangle. All right, so we're trying to prove that equation I labeled earlier. We're going to start with the tangent of alpha because that is our way to relate the purple triangle with the object to the blue triangle with the image. And so we see the tangent of alpha from the purple triangle is the object height to that distance x subscript o. And we see that in our blue triangle, the tangent of alpha is negative h sub I over xi. So we've got that negative height there. So I also want to point out that the distance xo is the object distance minus the radius. So the distance xo here, this purple distance, is this full object distance, and you subtract off the distance from the radius. That'll be useful. And then last but not least, I want to mention that the distance x sub I, the blue triangle distance, is equal to the radius, this whole r distance in red, minus the image distance, right? So what's what the x sub I is whatever is left over after you take the radius minus the image distance. So putting all of that together, we end up with the object height from this purple equation over object distance minus r from this equation equals negative image height from the blue up here divided by r minus s sub I, replacing it with xi. Make sure you're with me on that substitution. Pause the video if you need to before moving on. From here, we're going to do a little bit of algebra. And so what I did was I multiplied this, multiplied each side by 1 over HO to move it into the denominator of the right side of the equal sign. And I multiplied each side by r minus si so I can move that term up to the numerator on the left. After we've done that, we can see that this definition here, minus hi over ho, is the same as si over so. That's due to the fact that our magnification tells us that image height to object height is the same as image distance to object distance with a minus sign. And now it's a matter of a little bit of algebra. Multiply SO over to the numerator on the left, multiply SO minus R over to the numerator on the right, and you end up with the equation you see below there, that SO times R minus SO times SI is equal to SO times SI minus SI over R. Whew, we're almost there, folks. Our next step here is a little bit of adding like terms. I added SO times SI to the right to get 2SO SI, and I added the SIR to the other side of the equation. The next step after that is to divide everything by R. So we end up with image distance plus object distance equals twice the object distance times the image distance over the radius of your curved mirror. Dividing each side by object distance over image distance, we end up with image distance over the product of object and image distances plus object distance over that same product is equal to 2 times R. We are very close. We can now divide image distance on both from numerator and denominator. In this term, we can cross or cancel object and image distances in the second term. And then remember that the geometry fact in the last video is that the focal length, the distance from the focus to the center of, or to the mirror, is half that of the radius. Or in other words, the radial distance is equal to 2 focal lengths. Next, we've got 2 divided by 2, and we end up with our curved mirror equation. It is worth pausing the video right now. Make sure you're with me on each step. Rewind if you need an explanation of the video or an explanation of each step again, or feel free to ask me in class. All right, so we have our equation. We need to learn how to divide by 0 and divide by infinity when using this equation. So, the reason is far away objects, we will say they are at a distance of infinity, and sometimes we end up dividing by 0 also. So first, 1 over a really small number is a really big number. 1 over an infinitesimally small number is an infinitely big number. So that means that 1 over 0 is equal to infinity. Don't let your math teacher know that I told you that. Similarly, 1 over a really big number is a really small number. 1 over an infinitely big number is an infinitely small number. So 1 over infinity is equal to 0. And of course, for those of you who are in a calculus class, what I'm really saying is the limit as s approaches 0 of 1 over s is infinity, and the limit as s approaches infinity of 1 over s is 0. But we don't need to worry about that limit nonsense. 1 over 0 is infinity, 1 over infinity is 0. So that's going to be helpful in looking at object and image distances, because sometimes we get images that form infinitely far away, and sometimes we are trying to make images of things that are really far away. So some sign conventions for the mirror equation. That's the last thing we need to talk about. If the quantity is in front of the mirror, it is positive, and if it is in back of the mirror, it is negative. Now, what is the front of the mirror and what is the back of the mirror is arbitrary. So I'm going to choose the front of the mirror to be the side of the mirror that the object is on, and the back of the mirror is the other side of the mirror where the object isn't. Last but not least, your image height is positive if it's upright, and it's negative if it's inverted. And your magnification is positive if the image is upright, and your magnification is negative if the image is inverted. So the sign on the magnification or the sign on the image height tells you if you have an upright or an inverted image. Note, front and back are relative terms, but you must be consistent. If you call one side the front, the other side must be the back. All right, so that concludes this video. We'll do practice with this equation in class, making sure we're using the right sign conventions, making sure when we know if something is infinitely far away, so on and so forth.